Welcome to The Explainer. Today, we're going to peek inside an ordinary electrical wire to uncover a hidden world, a secret life, really, that was revealed by a simple experiment way back in the 19th century. And trust me, it changed physics forever. So here's our game plan. We'll start with the central mystery that had scientists scratching their heads. Then, we'll break down the incredibly clever experiment that cracked the case. After that, we'll get to the shocking discovery itself, see how it's literally powering our world today, and finally, we'll take a look at where the science is heading next. All right, let's jump right in. We're going to start by asking a question that sounds super simple, but it actually stumped some of the smartest people on the planet for decades. Yeah, we all talk about current, right? But what is that really? Is it a bunch of positive little things moving one way? Or is it negative things moving the other way? And seriously, how could you possibly tell what's going on inside a solid piece of metal just by looking at it from the outside? Now, what's absolutely wild here is the timing. People knew for a while that magnets and currents had this weird connection. But look at this. Edwin Hall did his big experiment in 1879, a full 18 years before anyone even knew the electron existed. He was trying to solve a puzzle without even knowing what the main game piece looked like. It's incredible. So this was Hall's big idea. He thought, okay, does a magnet just pull on the wire itself, or is it acting on the actual stuff that's flowing inside? He figured, if it's the charges, then the magnetic force should literally push them over to one side of the wire. And if that happened, maybe, just maybe, he could measure a tiny voltage building up on that side. If he could do that, he'd have his answer. So, how did this whole clever setup actually work? Well, it all boils down to one of the most fundamental forces in all of nature. In plain English, just think of it as a sideways voltage. It's kind of weird. You've got your current flowing forward, you bring in a magnet from, say, the top, and all of a sudden, a new voltage just appears across the sides of the wire. That little sideways potential difference, that's the Hall voltage. So the physics breaks down into 4 really simple steps. 1, you've got a current flowing. 2, you apply a magnetic field. 3, that field exerts what we call the Lorentz force, which is just the fancy name for the push that magnets have on any moving charge. And 4, that push literally shoves the charges to one side, they start to pile up, and boom, you've got a measurable voltage. Okay, this is where it gets really, really cool. That tiny sideways voltage wasn't just some neat little party trick. It was hiding a revolutionary secret about the nature of electricity. And here is the absolute genius of it. The direction of that voltage, whether the top side becomes positive and the bottom negative or the other way around, that's the key. It's a dead giveaway. It tells you, with no ambiguity, whether the things zipping around inside that wire are positive or negative. Now, this part can feel a little bit like a brain teaser, so let's walk through it. A magnetic field pushes moving charges sideways. So imagine negative electrons flowing from right to left. The magnetic force pushes them, let's say, up. They pile up on that top edge, making it negative. Simple enough. But what if positive charges were moving? Well, to get the same conventional current, they'd have to be flowing from left to right. And because both their charge is opposite and their direction of motion is opposite, the magnetic push is in the exact same direction up. So positive charges would also pile up on the top edge, but they'd make it positive. So all you have to do is measure the sign of the voltage on that top edge, and you finally know, for sure, what's really moving in there. And the result? It was absolutely stunning. For the very first time, Hall's experiment provided concrete, physical proof that in most metals, the electric current wasn't a flow of positive charges at all. It was a river of moving negative charges, the things we now call electrons. But here's where the story takes another strange twist. In some materials, especially these things called semiconductors, the voltage was the opposite of what he expected. It behaved exactly as if positive charges were moving. This bizarre result led to this incredibly powerful idea of holes, basically the absence of an electron, that act just like little positive particles. And that idea, well, it's the foundation of how all modern electronics work. So you might be thinking, okay, cool, 19th century experiment, but what's that got to do with me? Well, it turns out this isn't just some historical footnote locked away in a textbook. It's everywhere. Hall effect sensors are all over the place. They're in your car's anti-lock braking system, sensing the wheel speed. They're probably in your phone, telling it when you close a magnetic cover. In space, Hall effect thrusters use the same physics to propel satellites.
And what's really mind-blowing is that the same effect even helps astronomers understand how giant clouds of gas collapse to form brand new stars.
And you know what? The story doesn't even stop there. Hull's original discovery turned out to be just the beginning, the first member of an entire family of related and, frankly, pretty mind-bending physical effects. One of the biggest is the quantum Hall effect. See, if you get things super cold and blast them with a powerful magnetic field, the Hall voltage stops being smooth and continuous. Instead, it jumps up in perfectly precise, discrete steps. It's like climbing a staircase instead of walking up a ramp. This quantized behavior was so profound it led to multiple Nobel Prizes and is now used to define the worldwide standard for electrical resistance. Then you've got the spin Hall effect, which is something straight out of science fiction. This one separates electrons not by their charge, but by a purely quantum property called spin. It literally pushes spin-up electrons to one side and spin-down electrons to the other, and it does this without an external magnet. This is a huge deal for a future field called spintronics, which could lead to totally new kinds of computers. And to top it all off, in magnetic materials themselves, you find the anomalous Hall effect. In this case, the material's own internal magnetism creates an extra Hall voltage all by itself, giving scientists yet another tool to understand and engineer new magnetic technologies. So just think about the journey we've been on. It started with a simple, elegant question. What's moving inside a wire? And that one question didn't just give us the electron, it gave us the whole, which is the key to every computer chip on Earth. And it opened the door to this whole bizarre quantum world. It really makes you wonder, what other profound secrets are hiding in plain sight, in the materials we see every day, just waiting for someone to ask the right question?